Ok, I'm starting. Bem-vindos ao colóquio do Instituto de Física. Eu vou mudar para inglês, nossa convidada de hoje. So welcome. It's a great pleasure to have Ana Asenjo Garcia. Okay, I'm starting. Wait. Bem-vindos ao colóquio. Hold on, I have a problem here. Instituto de Física. Sorry. I had the YouTube video on, and so giving me a return. It's a pleasure to have Ana Asenjo Garcia from Columbia University, who will talk to us today. Ana is Spanish. She graduated from Universidad Complutense de Madrid, and afterwards she did a postdoc at the Institute for Photonic Sciences in Barcelona, and then joined Caltech as an IQIM fellow, later Marie Curie fellow, working in the group of Jeff Kimball, and I think with Derek Chang as well. She's received a Sloan Fellowship, NSF Career Award. Ana is a quantum optics theoretician. We've met only quite recently, but I guess we have a lot of common interests, and she will talk today about something she's been working on for quite a while, which is the collective interaction of atomic systems with light, a very interesting effect of this collective interaction, which is due to interference, superradiance, and subradiance, and how this impacts many-body physics, and how we can both learn and control many-body physics. So, Ana, I'm very, very happy to have you.
Thank you so much, Paulo. Thanks everybody for inviting me to give this colloquium. I'm really excited. Hopefully one day I can visit in person, not just on Zoom. So let me share my screen. Okay. So hopefully you can see my screen. So, well, as Paulo mentioned, I'm going to talk about quantum many-body physics with atoms and photons. And so this is kind of, I would say, the main focus of our research, the research in my group. So basically, what does this mean? I'm going to talk about collective light-matter interaction, and in particular, what happens when we have a bunch of atoms, or in general, any quantum emitter that is in some reservoir. So I'm going to basically talk about free space, but you can think about any other photonic reservoir. So you have a bunch of atoms; they can decay to this medium, and through this decay process, they are going to start talking with each other. So in general, we've been taught that dissipation, this process where, energy is lost to the environment and also information is lost to the environment, is bad. But if this radiative environment is shared among the atoms, then it's not that bad, actually. It can be quite helpful because now the atoms can become correlated through photon emission and absorption. And in particular, in free space, this happens whenever the distance between the atoms is smaller than the wavelength of the photons that are being emitted. And this happens because basically the field decays in free space. So if you have atoms really far away from each other, they should not talk to each other. But if they are reasonably close, we should expect that they interact collectively with light. So the main idea behind my talk is that in systems where we have many atoms sharing a radiative path, dissipation can be used as a resource. So when I was preparing, my class on quantum optics last year, I started reading the lectures of Glauber in Les Houches. Glauber won the Nobel Prize in 2005 for the theory of optical coherence. And the lectures are really amazing. So if you're interested in this, I really recommend them. But one thing popped out from the text, that is that he's talking about basically optics very generally. And he says that all the delicate and ingenious techniques of optics are exercises in the constructive use of noise. So this is precisely what my talk is going to be about. Because of the fluctuation dissipation theorem, one can think that one can read this phrase as, constructive exercise in the use of dissipation. So that's the idea behind my works. How can we use dissipation in our advantage? And so why do we care about this? We care about this because one of the main issues with quantum physics and quantum systems in general is that they tend to decohere. The quantum properties of these systems tend to wash away with time. And so the question is, can we prevent this process, or can we generate coherence via dissipation? In quantum optics, the question of how can we prevent the coherence takes maybe a slightly different shape. That is, how can we realize control interactions between atoms and photons? And this is important not because of just advancing our understanding of fundamental science, but also for developing applications such as, lasers or more efficient single photon sources. If we want to develop atomic clocks, if we think about quantum networks and we have to develop repeaters or memories, if we want to engineer protocols for quantum information processing, and also if we want to do quantum simulation or even quantum computing. So my claim here is that, well, there is a way of generating more efficient atom-photon interactions, that is by using actually atomic arrays. So let me talk about, this type of physics. So I consider the idea of doing quantum optics in atomic arrays a merge between optics and condensed matter physics. So back when people were studying, the beginning of quantum mechanics, when they started seeing that when electrons jump from certain energy level to another in an atom, they emit discrete packets of energy, right? The energy is quantized, and they started seeing this emission spectrum. And so this ties the origin of quantum mechanics with the question of what is light. And so once they started thinking about, well, let's develop the model of the atom, let's try to understand the dynamics of electrons in an atom, then you can go in two directions. And this is what the physics of the 20th century has been about. The first one is you might consider, what is the dynamics of electrons when you put many atoms together. So now you have a crystal. So for instance, here, I just took a picture of graphene. And so you have now a crystal of atoms, and now the electrons are hopping between the atoms. And in principle, you can think about the single electron properties that are derived from the band structure of the electrons, or you can also think about correlated physics that comes from the electron-electron interactions in these materials. So this gives rise to new materials and new physics. Then there is another, other type of questions that you can ask, that is, what happens with the light? And so this has been also explored in the last century. People have investigated the development of which types of light you can generate from matter. So this has given rise to generation of coherent states of light, like lasers, and also of quantum state of light, like single photons. And they have developed really exquisite techniques and control to study the interaction of light with a single atom. So while this is, in my opinion, very exciting science, it's the control of these systems has been, or the attention in the systems has been mostly devoted to what happens, for instance, for a single atom in a cavity. So one optical mode and one atom. And now you can ask yourself, what if we merge the two things together? So what if we have now an array of atoms, and we're no longer going to care about what the electrons are doing. We're going to care about what the photons are doing. So now we have some sort of condensed matter system, but where the physics that is going to be of interest to us is that of the photons, okay? So now we have this kind of a Wild West type of a scenario, because we have many atoms and potentially many optical modes in free space that these atoms can radiate into. So let's see if we can, put a bit of order in this complicated problem. So I wanted to talk about what are for me the most important differences between the optical and condensed matter systems. So here I have a representation of a wire that you apply some potential and the electrons are going to start flowing, okay? A similar type of experiment would be that of, for instance, a fiber where you shine some laser and now photons propagate through the fiber. So an important difference is that the photonic system is intrinsically driven. You have to put you have to drive it with some laser, and this field is going to be oscillating with a frequency omega. Okay, another important thing is that photon number is not conserved. This is associated with the fact that electrons have charge and photons do not have charge. So basically, imagine that you have a defect close to your fiber. So as the photons propagate through the fiber, when they see this defect, they can be transmitted, they can be backscattered, but they can also be emitted into free space. This is a process that is not possible for the electrons. The electrons will either pass or they will be backscattered, but there is no density of states for the electrons to jump out of the metal. However, there is density of states for the photons to do so. So what happens is that photons may leak out, and then the photon number is not conserved. So it means that photonic systems are inherently open. And it also means that we're going to have some sort of conflict between controlling our system, for which we need to access it and drive it, and the issue of dissipation, that we're going to be losing photons. Another important difference is that of interaction, okay? So photons basically do not interact with each other versus the situation of electrons. So electrons, they're gonna see each other through the Coulomb interaction, and this is going to produce correlated physics. Electrons can become correlated through the interactions. Photons, in principle, if two of them cross in a fiber, they barely see each other and they do not interact with each other. So to make them interact, we need to interface them with matter, and in particular with atoms or the other types of emitters. So you can think about what would be an ideal light-matter interface to, combine the best of both worlds. We want something that is strongly non-linear because we may want to produce interactions between photons, for instance, for processing quantum information. And at the same time, we want to control the dissipation. We don't want things to be radiating like crazy, okay? So you can ask yourself, well, okay, let's design such a thing. What is the best idea I can come up with? So the first idea is, well, I'm gonna forget the idea of arrays. That's too complicated. I'm gonna just look at a single atom and see how a single atom does as a light matter interface. So a single atom, in general, an atom may have many energy levels, but under reasonable approximations, it can be approximated as a two-level system with some ground state and some excited state that has, an energy gap between them. So if I shine a laser to such an atom, the electron is going to be promoted from the ground to the excited state. And because of the unharmonicity of the atomic potential, there is going to be the second photon. If I send a second photon, it cannot be absorbed again. So the spectrum is very different from that of a harmonic oscillator. So in some sense, this is really good because it's a strongly non-linear medium. So the fact that an atom has interface with a photon changes the behavior of this atom to a second photon. That's good. But it has an issue that is when the atom is in the excited state, this excitation is going to live for a finite time. That is the inverse of the spontaneous emission rate, gamma zero. And when it decays, it's going to decay very broadly. It's going to radiate as a dipole. And so we're going to have photons all over space with a dipolar pattern. This is also related with the fact that if you have an atom in free space and you send a laser to this atom, this coupling between a photon that travels in this beam and the atom is really small. And the reason for that is because the probability of interaction is given by the absorption cross-section of the atom, and that scales as the wavelength of the photon squared, and it's divided by the mode area. And so due to the diffraction limit, we cannot arbitrarily focus a beam to a tiny point. And so this means that this ratio is very small. The probability of interaction is tiny. So, okay, a single atom doesn't seem to be a great light-matter interface. Then let's just increase atom-photon interaction. And so the answer on how to do this was given to us by Purcell, when he realized that the decay rate of an atom depends on its environment. And so we can change the environment. Changing the density of optical modes will change the way that atoms decay. It can enhance the decay of the atom, or it can inhibit the decay of the atom. So you can think again of having an atom. This atom is in some environment that is vacuum. And as I've said, this atom is going to decay if it's in the excited state, and it does so at a rate that is given by the spontaneous emission rate in vacuum, gamma zero. And gamma zero depends on the medium through the Green's function of the medium. This is the fundamental solution of the wave equation. It's just the propagator of the field, okay? So if now we change the boundary conditions, such as, for instance, we put a mirror, then we're going to change the propagator of the field, and thus we're going to change the emission rate. And so now we can change how our atom talks to the optical modes. So this is what people have been exploiting for decades now when they put atoms in cavities. So there is a whole field of cavity QED where people place atoms in between two mirrors. And here the idea is that you want to enhance the interaction of this atom with this optical mode, the optical mode given by the cavity, versus the decay into any other mode that is not the cavity mode. So if you design your cavity right, this rate of decay into the cavity can be much larger than the spontaneous emission rate into vacuum. And this is given, the ratio of that is given by the cooperativity. So if you have designed your cavity right, that cooperativity can be very large, and that gives you an efficient light-matter interaction between the cavity mode and the atom. More recently, people have been looking at waveguide QED. This is another paradigm, but it's more or less the same idea. So instead of having an optical mode given by the cavity, the optical mode that is relevant now is that given by a 1D photonic reservoir. So like, for instance, a waveguide, and you place your atom close to your waveguide. And the idea behind this game is that you want to maximize what is called the optical depth, that again is the probability of decaying into the waveguide versus free space. So just as an example, I wanted to show you some pictures of experimental realizations. People are able to trap atoms close to fibers quite regularly. Here, this ratio of the optical depth is very tiny, 5%. So it means that when I send an atom, a photon through the fiber, the chances of losing it are actually 95%. With 5%, it goes back into the fiber and actually produces, it's reflected. People have looked at atoms in photonic crystals. In that case, the group velocity of this structure for the photons is slower. So the interaction time with the atoms is higher. And then this optical depth figure of merit is higher. Similarly, people have looked at other type of emitters. So the first example here is that of a quantum dot with a photonic crystal. And so because the quantum dot is it's an artificial atom and it's embedded into the crystal, the figure of merit is much larger. And then the system that currently displays the larger optical depths are that of superconducting qubits coupled to transmission lines. This is not an experiment that is done at optical frequencies. This is at microwave. And so basically these superconducting qubits are very efficiently coupled to the transmission line. And this means that the decay rate of the qubit versus any other parasitic decay rate is 100. So it's actually, if you send a photon through this waveguide, it's going to almost deterministically interact with the superconducting qubit. So, okay, so I have said that people have been very creative in tailoring the environment of the, around the atom. But we could, go a step further and say, well, we might as well use other atoms as environment. So instead of having a situation where we have an atom coupled to a fiber, what if we make the fiber out of atoms? What if now we're gonna bank on collective phenomena to make the interaction between, this atom and this effective waveguide much larger. Is this possible? The answer is yes. And this is because when we have atoms in arrays, they are able to guide photons. And so, as I've said, if atoms are very far away from each other, they will radiate photons away. So the whole array will be very dissipative. But if the atoms are close enough to each other, they support what are called guided or dark modes that do not decay. So they would truly behave as a waveguide. And these dark states can be used to improve the fidelity of some quantum applications such as memories and clocks. So I won't be talking about that today, but if you are curious about this, here are a couple of references. So is this all science fiction? I guess is the next question. And the answer is, I believe it's not. And this is because in the last 5 years, people have been developing this type of experiments where they are able to trap atoms with optical tweezers and place and generate ordered arrays of them. So this is an example of a 1D array of atoms. So every point you see corresponds to an atom, to the fluorescence of a single atom. This is an experiment that was done in Harvard. This is an experiment where they arrange atoms in 2D, so in different types of shapes, from a square to heart shape, I guess. This is an experiment from the group of Antoine Brouwer in Paris. And this is, this is taking it to the limit in 3D. They are able to do an Eiffel Tower. So they are a French group, so they wanted to show the national symbol. So given that these experiments are happening nowadays, one can ask, we know that if now we're sending light to these type of structures, this interference in photon emission is going to lead to correlations between the atoms. So what is going to happen? What is going to happen at the single photon limit, where we have one photon shared among all the atoms and we have linear type of physics? And what's going to happen in the other scenario where we have many, many excitations and there's going to be strong correlations, and this is many-body physics with atoms and light? Okay, so these ideas have started to be exploited in 2020. So I wanted to show you a couple of experiments. So the first one is performed by the group of Manuel Bloch in Germany. So they send light to a 2D array of atoms that they have trapped using an optical lattice. And when the distance between the atoms is smaller than the wavelength, this 2D array should behave as a perfect mirror. So in the experiment, they measure the reflectance as a function of the detuning between the laser light and the atomic transition, and they see a reflectance of 60%. So there are experimental, imperfections, but still a single a layer of atomic thickness can behave as a mirror, with 60% efficiency. So it's quite impressive. And the second experiment is that of the group of Antoine Brouwer in Paris. And in this case, they had an array of 1D array trapped with optical tweezers, and they send light, and then they see collective frequency shifts in the light that arise from interactions between atoms. Okay, so here is what I'm going to be talking about in more detail. I'm going to talk about, this idea of waveguide QED, but realized with atoms. So I'm going to focus on single and few photon physics in atomic chains, and then I'm going to go to the extreme limit of many photons in atomic arrays, and I'm going to discuss Dicke superradiance. So if anybody has a question, now is a good time. If not, I will also be stopping, right after I cover my first topic. Okay, so if there is no questions, I guess I can continue. Okay, so I'm a theorist, so I'm just going to show a couple of slides with a bunch of equations, but I should be done soon. The first thing that I want to mention is how are we going to treat this problem. So we have, as I said, a bunch of atoms. They are in free space. How these creatures interact with each other. So we can consider that basically when we send light to an ensemble of atoms, light is going to induce a dipole moment in them. They are going to start radiating, okay? And these interactions between the atoms, so when atoms scatter a photon, the photon can be absorbed by another. So this is going to be mediated by photons. And what we're going to do is we're going to integrate out these photons. And now the effective interaction is atom-atom interaction, and is mediated by the Green's function of the medium, that is the free space Green's function. So once you do this, you end up with a situation that describes this open quantum system that is given, the evolution of this system is given by an equation for the evolution of the atomic density matrix that is proportional to, it has a coherent or Hamiltonian term, and it has a Lindblad term that accounts for dissipation. Why is there dissipation in the system? Again, because, atoms may radiate and the photons may never come back to the atoms. So then this is a purely dissipative process. So the coherent interaction is given by this expression. So here I'm saying that these are the atomic coherence operator between the excited and the ground state. This equation just says that, atom J is going to decay to the ground state and a photon is going to be picked up by atom I. So basically this type of flip-flop interaction, okay? And the dissipative part of this equation reads like this. So this is the Lindblad operator, okay? And as you can see, these coherent and dissipative parts are proportional to the Green's function. That is the propagator of the electromagnetic field. And again, it's determined by the environment. So if you are condensed matter theorist, it might help you if I say that this is a long-range XY model. At the same time, it's different from a traditional condensed matter system in the sense that it's open. So the behavior is stochastic because photon emission may occur at any random time. And at the same time, it's also a many-body problem because we have a dimension of the Hilbert space that scales as 2 to the n, where n is the atom number. So in principle, keeping track of these dynamics is exponentially hard. So what we can do, and this I'm gonna build up to the end of my talk, is we're gonna look at subspaces, different subspaces of excitation. So what happens when we have just one single excitation shared among all the atoms? What happens when we have two? And then in the typical, physics example, 1, 2, n, right? So this is exactly what I'm going to describe. So, and I'm going to show the example of a 1D array because it's the easiest to comprehend. So now we're going to have a 1D array. The atoms are separated by a distance d, okay? The resonance frequency of the atoms is given by omega 0. And now we can, in this simplified version of the problem, when we only have one single excitation, we can describe the dynamics using a non-Hermitian Hamiltonian, where I have combined part of the coherent interaction and part of the dissipative interaction. And here I have just a Green's function that is a complex number, okay? So the Green's function in free space is kind of a textbook problem. And this is the equation for it, okay? So nothing special, it has some, maybe it just describes the radiation of a dipole in free space. So now I'm going to look at the case of an infinite chain. And now then I can diagonalize this problem using block waves. Now I'm going to have spin excitations in my atoms that are characterized with a wave vector along the direction of the chain and are superpositions of a given atom being excited while all the others are in the ground state. And so these collective modes are going to have some frequency, some dispersion relation that is going to have kind of two components. One that is just, the actual frequency, energy of the excitation. And the second part is the decay rate, because again, this Hamiltonian is non-Hermitian, okay? So basically what we're doing here is we're looking at a band structure, but it's a special one because we're going to have radiative modes, or part of our band structure is going to be decaying these states. So if we do that, and we can plot the dispersion relation, versus the wave vector. This is the result, okay? And so let me describe what this means. We're going to have a region in our dispersion relation that is the non-guided region. So here, these states, even though I have drawn them, they have a finite lifetime. So if you prepare them, they are going to decay in a time that is of the order of the spontaneous emission rate into vacuum. So, you don't have to wait very much and these things are gone. But then there are like truly, long-lived modes that are what are called the dark modes or subradiant or guided modes that live beyond the light line. So what is the light line and why are these modes dark? The reason is because if you think about the wave vector of these states, they lie beyond K0. K0 is omega 0 over c, so it's the maximum wave vector that a photon can have in free space. So these states, because they are confined to 1D, they have a wave vector that is larger than any wave vector for a freely propagating photon. So they have to be confined to 1D. And the reason for this is that if Kc is larger than K0, then the perpendicular wave vector has to be imaginary to compensate. So these are evanescent modes that are, constrained to this chain. And so they are truly guided modes. And in this case, it's just an atomic excitation that kind of jumps from one atom to the other. And you may ask yourself, does this happen, for any distance? Obviously not, because I said before, if atoms are very far away from each other, they should not see each other. They should radiate as independent dipoles. Of course, you cannot have modes that exist forever. So when does this happen? This depends on the dimension of the array. In 1D, it occurs whenever the distance is below half of the transition wavelength. So it means that we have this now band structure that has dark modes and has bright modes. And so you could ask yourself, what can we do with this? So one option is, well, we can, as I said before, we can use this as a quantum waveguide. We could imagine putting an impurity atom next to our chain. And I said before that Purcell told us that the decay rate of an emitter depends on its environment. So it means that now we can integrate all the atoms and think that these atoms are a bath for the additional impurity. And if you start putting more and more impurities, now, you're going to have impurities connected by this bath, and you do effectively atomic waveguide QD. So you can start playing all the tricks that people have been doing in quantum optics, but without any type of dielectric. And this is all thanks to the magic of interference. So I just wanted to mention that besides our suggestion, these ideas have been extended recently to other dimensions. So people have looked at what happens when you put emitters in to the arrays, what happens when you have impurities now in 3D arrays, and even what happens when you put them in rings. So you may imagine that by changing the dimensionality and the geometry of the array, you may realize different dispersion relations, and this produces that these emitters are going to talk to each other in different ways. Another thing that you can do is you can trap and release these atomic excitations. So the idea is that if you have a photon propagating through a dielectric, it's really hard to change the properties of the waveguide, of this dielectric waveguide, fast enough to trap it. But, atoms are special. So in principle, one can think of using some dressing field in this atomic chain. In this case, we have to use a elliptically polarized dressing field and atoms that have multiple levels, but that's not very relevant. The important thing is that by doing this type of procedure, we can control the transport of these speed excitations. And one can think of, well, I'm gonna input some, photon that is going to travel along my chain. And by using this dressing field, I'm going to change the dispersion relation in real time. And so now I can trap my photon. So the photon propagates, I start playing tricks with my dressing field, and my photon gets trapped until I want to release it, and then it continues. And I can do something similar where I let my excitation propagate, I play similar games, but now I send it back. So it's a way of controlling in time the transport of excitations and also trapping excitations, because again, they cannot leak out to free space. And I'm just playing with their with the band structure of the collective modes. And so everything I have said, even though I have mentioned the word atoms many times, is actually classical physics. Because it's all banking on interference. So one thing that I did is I looked at all these collective phenomena for atoms at the single excitation level. It's just the physics of dipoles, dipole interactions, antennas. So you can have these at many wavelengths, many sizes. And the earliest example I found of kind of collective interference to direct light in certain directions and so on is in this example, where there's a huge radar that Nazi Germany built in 1944 to detect planes coming from the enemies. This massive array of antennas, 30 meters by 16 meters, so it's pretty massive. You can make this smaller, going to the optical domain. This is an example of phase arrays, courtesy of the Lipson group at Columbia, where you have a bunch of waveguides, and you can control the phase of each waveguide such that now you can direct light in any direction you want. And you can even think about what's the tiniest possible phase array or antenna that I can build, and it's made of atoms. And this is an example of these modes, guided modes that I was mentioning before. They are dark in the bulk, there is no radiation, and they can only radiate in the tips. So other types of modes would radiate with other spatial profile. But again, this is the physics of antennas, just very small antennas. But of course, I've been talking about many body physics and many excitation physics and quantum physics. So of course, this changes when you have multiple excitations. And this is what I'm going to talk about next. So the first thing that I want to talk about is what happens beyond one excitation. And this is with two excitations. So people have been exploring how to generate nonlinear optics between single photons, okay, in atomic physics systems for a while. And the conventional idea is to use an atomic ensemble that you can control its transitions. And so basically you have photons driving this first transition in red. And then with a control laser, you promote some atoms to a Rydberg state. So a Rydberg state is like a massive superatom that doesn't allow other atoms to be excited at the same time when they are in the Rydberg state. So this produces blockade between photons. And this is the conventional idea. So you basically create a transparency window where photons can propagate in this atomic media, promote some atoms to this Rydberg state, and that makes photons collide and changes the statistics between the photons. In atomic chains, we do not need Rydberg. And this is because we have this hardcore nature of the two-level systems that we can bank on to produce interactions between photons. And so you can imagine what would that be? So you have a chain, you have two spin excitations that you have promoted into or generated in the chain, and they start propagating and they are going to collide. And then, a single atom cannot be excited twice. So this means that these pulses have to be distorted to accommodate for that constraint. And so that generates interactions between these pulses. And the character of the interaction can be either more dissipative or more dispersive with the lattice constant. So this is just an example of the population in the chain as a function of time. For very small chains, the interaction is coherent. So there is a phase change, but there is no population. There is no population decay. It's not dissipative, it's coherent. If you increase the distance between the atoms, then as they collide, the population drops. So when they collide, a significant fraction of the excitation is radiated out. And this is just because the distance between the atoms controls how many of these collective modes fall inside the radiative region or outside, and they are dark. So you can think of, well, if we use these small distances where the interactions are coherent, you can use these to realize conditioned phase gates for quantum computation. Okay, so this is just an example of, eventually if you prepare some state, this state after interaction is going to pick up a phase. And this is the accumulated phase that it tends to pi in the limit of very small lattice constant. So pi phase shift is what you would need to realize one of these condition phase gates. Okay, so this is another stopping point in my talk. So if you want to ask a question, this is the time. If not, be prepared for, what happens when you have many photons, the most, extreme case.
Anna.
Yeah.
In this case where you just spoke of having a conditional phase gate, this is conditional one photon interacting with only one other photon, and would you have like a single photon phase gate?
I mean,
you have numbers for that?
Sorry?
Would you have a single photon phase gate?
You would have, the idea here would be if you just have a single photon, right, it would propagate. It's like the matrix that you will build for your gate is like, I have 0 photons from both sides. I have just one photon that just propagates and picks up a phase. I have another photon that propagates and picks up a phase. And when the two of them are together, then you have an additional pi phase that is acquired. And with that, you can build a 2 photon phase gate. So this is what you need in principle for computing. I don't know if I answered your question at all.
Yeah, okay. So it's a conditional phase gate.
Yeah, it's because the other one, so one picks up a phase condition on the other existing or not. Yeah.
Right. And I suppose also that this is interchangeable, meaning that the control bit or the target would be interchangeable.
Yes, exactly. And then, if I haven't explored this at all, but you can start doing like more fancier games, like you have dual rail, or like you have a beam splitter, all that. So it's something that we haven't really explored, but in principle, you could think about how to do that. But to be honest, there is an issue that is these long-range interactions actually that happen. So you don't have the interaction, not only most of the interaction happens because you cannot put 2 atoms on top of each other, but there is also a bit of interaction because of this near field interaction between the atoms. So these kind of more longer range interactions mess up your pi phase shift. So you don't have a pure pi phase shift. You have something that may approach a pi phase shift, but it's not exactly a pi phase shift. So it's not like the fidelity of the gate is not perfect. Yeah.
Thanks.
Okay, so now I'm going to talk about the most extreme case, that is, what happens when I have many photons in my array. And so this is the situation that deviates the most from ideas in, for instance, condensed matter physics, where, electrons are confined to the material. Here, we're going to have photons jumping out of our array. So in this case, when we have many, all the atoms excited, there are going to be very few dark states. So dark states, as I said, you can understand them as these spin waves with a given wave vector. And so if I start piling a lot of excitations in my chain, I'm not giving them enough space to exist. So everything has to be radiated. The most extreme case, as I said, is that where all the atoms are in a product state of all of them being excited. And the question is then, what happens now? And this is an important question in quantum optics because it's connected with, it's actually the question that Dicke asked and answered in 1954. That is, it's he posed this question in this famous paper, and I really like the abstract of this paper. So if you read it, so let me read it, at least a bit of this abstract. So it says that in the usual treatment, a bunch of molecules, these molecules radiate independently of each other. However, this simplified picture overlooks that the molecules are interacting with a common radiation field, and the model is wrong in principle. So then, it's a very strong abstract, and he's totally right, and he goes and tries to answer this question. And so what Dicke realized is that when you have many atoms together, these atoms and many excitations, they do not just radiate more, they radiate differently. Okay, so what does this mean? If you look at the photon emission rate as a function of time, if you have atoms that are decaying, that they are not correlated, for instance, far away from each other, they would decay in an exponential manner, boringly, Then what if they are all very close to each other together, or in the case of Dicke, in a cavity, okay? Then what happens is as they start decaying, they start in a state that has no coherence, okay? There is no dipole moment. This thing should in principle not even radiate to begin with. It does only radiate because of quantum fluctuations. So these quantum fluctuations drive the atoms out of this initial state, that is the product state, and they start radiating. And as they radiate, they start to become correlated. They synchronize. And so this process of synchronization through dissipation gives rise to this very large macroscopic dipole moment that radiates a burst of intensity, and then they decay. So this is the photon burst of Dicke superradiance. So as I said, this is an example of emergence of macroscopic coherence through dissipation. You could ask, well, Anna, why are you even interested in this, given that Dicke already solved it? The caveat is that Dicke solved the problem in a cavity. So this is exactly as if all atoms are exactly at the same point, because they all talk to each other at the same rate. So this is provided by the fact that the cavity has just a single optical mode. So this problem has a extremely high symmetry because of these, all the interactions between the atoms being equal. And so it's solvable. But anything that breaks the symmetry makes the problem extremely hard, because again, you have to calculate these dynamics in this exponentially large Hilbert space. And so the question now is what happens for extended arrays? And this is a question that people have asked in quantum optics during many years. And there is no, at least to me, any clear consensus of, what destroys superradiance, will superradiance survive in extended arrays or not? So what is the question that we're going to try to answer? As I said, if the atoms are very far away from each other, we should expect this kind of boring exponential decay in how they emit photons as a function of time. On the other hand, if they are all very close, very, very close to each other, they should produce this burst in radiation where the maximum of radiations happen at a time that is different from zero. So there has to be a transition between this behavior and this behavior. And the question is, when does this happen? At what distance? What is the critical distance where the burst doesn't exist anymore? And so you could try to answer this numerically. So we did that with different geometries. So this is a chain of atoms, this is a ring of atoms, and this is a 2D array. The issue is that we can only do that for 16 atoms. And this is again because of this, exponential growth of the Hilbert space. Our computer is not good enough. And even if you had the greatest computer in the world, you cannot do this for many more atoms. And so you're really, really limited, because if, for instance, in 2D, this is a 4x4 array. So it's not very extended. So one thing that I also wanted to mention is, as I said, here we have an interaction that is given by a Hamiltonian and this Limlat operator that carries the dissipation. And people were thinking that superradiance was destroyed because of the presence of the Hamiltonian. The Hamiltonian and the near field interactions were thought to cause dephasing. And so what this plot shows is that whether you have Hamiltonian or not, there is not a significant change in superradiance. So superradiance is going to die, but it doesn't die because of the Hamiltonian interaction. It dies because of other reasons. And so then, given this sad state of affairs of numerical computation, you could ask yourself, is this all we can do? And the answer is no. We can try to understand what's going on, and this is gonna allow us to understand the problem better. So, as I said, this is a hard problem. So why is that? So the initial state is that all atoms are inverted. Initially, as I said, there is no coherence. This is a state that has not a superposition or entangled state. There is no the expectation value of the dipole operator is 0, there is no coherent, it should not radiate. But they start decaying the atoms due to vacuum fluctuations. So again, this is an equation like the one I wrote before. It's just that now I have diagonalized this part in terms of collective modes, okay? So these collective modes are what are called the jump operators, where an atom jumps from the excited to the ground state, but because now I have diagonalized it, these are now collective. So when a jump operator acts on my system, then a photon is emitted, but it's emitted from a superposition of the atoms. You don't know which one emitted it, okay? And each of these jump operators acts with a given rate that is, you know, is given by this command. So let's see how this problem is complicated. We know that if the lattice constant is 0, the problem becomes symmetrized. And the number of states that matter are only the symmetric states. And this means that we have a burst because Dicke told us so. If we have a lattice constant that is infinite, also the states are uncorrelated and the decay is exponential. But if we have a finite lattice constant, it's not clear what is going to happen, and the complexity of the problem scales exponentially with atom number. So we could think about how to reduce the complexity, and the way is to just look at the early dynamics. So one thing that happens is that the atoms start synchronizing at the beginning or not at all. So you can start looking at the dynamics here, and if you know the derivative of this curve is positive at t equals 0, it means that there is going to be synchronization. And if it's negative and things decay, there is no way that things are gonna get better. So either they synchronize in the beginning or they never synchronize. So given that knowledge, we can think about what is the minimum burst that can happen. The minimum burst is such that the first photon that is emitted enhances the emission of the second photon. And so we can calculate that by looking at the second order correlation function that is calculating the probability of emitting 2 photons versus the probability of emitting 1 photon squared. If this is 1, it means that there is going to be this minimum burst. The second photon is enhanced because of the first. And then, you know, we're going to have superradiance. And if not, then we're going to have something that decays exponentially. And so when you do this calculation, which I'm not going to detail here, you realize that the answer is that it all depends on the variance of the eigenvalues, the variance of the collective modes. And you find these collective modes by diagonalizing a interaction matrix that is given by the imaginary part of the propagator, the Green's function. And this scales is an n by n matrix. So there is no 2 to the n, there is nothing like that. It's an n by n matrix. And it means that we have gone from something solving this dynamical equation in an exponentially large space to diagonalize a much simpler matrix. And this equation is universal, is valid for chains, for 2D arrays, 3D arrays, etc. And what it means is that the variance of these eigenvalues to be much larger than 1, what does it mean? It means that there has to be a dominant channel of decay. In the case of Dicke, where all the atoms are in a cavity, there is only one channel of decay. You can only emit a photon into the cavity mode. In the case of an array, in principle, you have many, decay rates or many decay channels that may have significant probability of atoms decaying into them. But we have said before that if we place the atoms close enough, many of these channels become dark. So this is the perfect situation because it means that now from all the channels into which our array can emit, we're only going to have very few of them that matter because all the others, the emission is suppressed because of destructive interference. So instead of constraining our number of decay channels externally from the imposing boundary conditions, we're going to do so based on the geometry of the array. So, well, this is just a plot for you to believe me. This is just that the time of the peak of the emission rate, the maximum, happens at time different from 0 whenever the second order correlation function is larger than 1. So this is a good figure of merit to characterize superradiance. And so given that, we can calculate now, what happens for whether we have a burst or not. for very large atom numbers. Actually, here we have shown, I'm showing you 1D chains, but we have done even 3D arrays with 10 to the 8 atoms. This is impossible, obviously, to solve dynamically, but our equation holds. So we can, this is the region for which the distance is below that will show, the array will show superradiance, and distances above that, this the fact that you have many channels that are now all contributing similarly are going to wash away superradiance. So basically the conclusion is that Dicke superradiance is a universal phenomenon. It doesn't just happen for very tiny clouds of atoms or for atoms in cavities. It happens for any array as long as the lattice spacing is small enough. And in 1D, this means 0.3 the wavelength of the photon, but in 2D, it is actually a critical distance. So it's like for any distance you want, but for any reasonable size of array, it's like 0.8 lambda. And for 3D, we have seen that there should be bursts for distances above lambda. So with this, I wanted to finish because I've been talking for a really long time. I just wanted to say that I find this interesting because it's a problem that is in some sense basic, electromagnetism, but it's complicated because of the quantum mechanical aspect of it. So it's trying to understand the physics of correlated quantum dipoles, but this involves having dissipative interactions and also long-range interactions. It's a new playground of multidisciplinary physics, so you can start adding even additional complexity. So, like for instance, motion in the atoms, and things that we want to study include, producing different type of dispersion relations, looking at higher dimensions and see how, how the dark modes behave, how the bright modes behave. We want to keep exploring this idea of coherent control of single photon states, how to trap excitations that propagate in our systems, and how to generate photon-photon interactions and gates. And the last thing is that this idea of superradiance in some sense is very broad because it's an example of self-organization, but through dissipation. So I'm really interested in understanding what happens in higher dimensions, including, for instance, the multi-level nature of atoms in our calculations, and try to understand what is, the role of putting atoms in a cavity versus free space. Can we do things like superradiant lasers without mirrors? And can we control the dynamics of, this stochastic many-body dynamics by using things like measurement and feedback? So I think it's a cool problem. And so with this, I wanted to acknowledge everyone that has been involved in this work, both my postdocs at Columbia, Stuart and Ricardo, and also our collaborators in France, Antoine and Igor, and Lisa Orozco, who is our collaborator in the University of Maryland. And if you're interested in kind of single particle physics or single photon physics, you can browse these couple of papers. And if you're interested in the many-body physics of this problem, the details are here as well. And so thank you so much, and I'm happy to answer any questions.
Thank you, Anna. Thank you very much, actually, because I thought it was very instructive and exciting. So we are open for questions. I already see Marcelo has his hand raised. So Marcelo, please.
Thank you very much for the presentation. It's a really nice talk, very stimulating, and I believe that students profited a lot of it, as all of us. And some questions rise, like, okay, first, from the experimental point of view, applications. Would there be any implications of these techniques of basically this reservoir engineering for metrology that are envisaged for these for specifications?
Yes.
And another one, given that you get a nice system that can, it's a hard problem, but with a smart way you can begin the solution and see the evolution, could be used as a sort of certification for quantum computing protocols.
Okay, those are hard questions. Okay, so the first question with respect to applications. I think there are multiple applications that one can think of. The first one is memories. This I didn't mention very much, but the fact that you have dark states means that if you want to store a photon, so typical like EIT protocols for storing photons work in the following way. You have, for instance, a waveguide, you have atoms, photon comes, this drives some transition in the atoms, and with some control field, you store this photon into a collective spin excitation in the atoms. But then when you do, so that's the storage, and the retrieval is you do the time reversal process of this. So you come with the control field, then eventually the photon is gonna leak out into your waveguide. But of course, in this process of leaking out, it can be leaked out into the waveguide or leaked out into free space. If you now realize that you can have dark state to free space, now the scaling the fidelity of this protocol, instead of scaling linearly with atom number, can scale exponentially with atom number. So you can do much better with very few atoms just by protecting the emission such that it's only going into the waveguide. So that's the first thing. You said, okay, more applications. So another application that I can think of, this complicated application actually, but it might work, is, you know, you have this, the dynamics is very complicated, right? You have photons that are being emitted. You, in principle, don't have control over your system, but you might ask yourself, and I don't know the answer of this, the following. So when one of these jump operators, so basically whenever a photon is emitted, you lower the atomic excitation by 1, and you go into certain state. And so it's very probable that the state to which you're going is a superradiant state. So it's gonna live for a very little time and it's going to continue decaying. So it's like a cascade process. So in some sense, okay, you have started from a state that has no coherence and you have produced an entangled state. It's definitely an entangled state. Issue is it's gonna live very, very little. So it's of very little use, right? So what you could think about doing is, okay, if you can detect the photons, and these jump operators, they have some patterns in the atom, but they also have its own far field pattern. So they would correspond each of them to some specific far field pattern. So if you get the right far field pattern, so if I detect a photon here and here, for instance, so they are correlated photon emission, then I know which jump operator has acted. If the one that has acted, I don't like it, then I can potentially illuminate my atoms again, revert to the initial state, and do this many times until the atoms decay using one of these dark collective modes, and then they are trapped in a dark state. So this will be an entangled state that is dark and lives for a very long time. So it's a way of doing kind of feedback to produce entangled states. So it's another way. And then the thing that I would be very interested in trying to understand is what happens if you pump the system. And well, these dark states in principle, they might find use in metrology. Then one other thing that I think is interesting is what happens when you pump the system. And again, the emission is, because of this interference, emission can only happen in certain directions, or I mean, not can only, but is favored in certain directions. So can I have a situation where, most of the photons are always emitted in certain directions? Also, what's the statistics of these photons? So can I generate like correlated photon states? Can I generate a laser without mirrors? I don't know. So I think these are cool questions that I haven't answered yet, but I think there are many applications. And then, I mean, of course, in general, for realizing any light matter interface, having many atoms and destructive interference helps, because the efficiency of the interaction between photons and matter is going to be enhanced, because basically you're suppressing emission into modes you don't care and enhancing emission into modes you care about. So you can, in principle, do everything that people do in cavity QED or waveguide QED better using arrays. And then you asked something about quantum computing. I mean, I think it's too complicated. I mean, I would not use superradiance as a way of doing a quantum computer because it's a dissipative process. So it doesn't seem to be the way of computing. But in principle, you could think about, there are many ideas of not so much quantum computing, but quantum simulation, where you put atoms in like 1D or 2D photonic crystals, and they are interacting evanescently when the atomic frequency is in the band gap. So there is like no actual photon emission, it's just non-dissipative interaction, just coherent. And so you don't need a photonic crystal for that. In principle, you could do this with an array of atoms. And this is something we proposed in 1D, and these ideas of extending it to 2D and 3D go along the same lines of, can we use arrays of atoms as media to produce the right interactions to use for quantum simulation? Quantum computing, I think you could do gates. In principle, I think there is actually a recent paper by the group of Ignacio Cirac where they started looking at gates in arrays. And so there is also this idea of phase gates. But superradiance and quantum computation, I think they don't go together.
Okay, thank you. I was more thinking of using the system as a process that would evolve in a predictive way, and then try to make a quantum computer simulate this evolution, maybe as a certification for a universal quantum computer or a tool for certification.
I'm not saying it's not possible. It's I would need to think about it more. Yes.
Okay, thank you very much.
I have also a few questions that I'm just waiting to see if there are any other questions from the audience. Otherwise, I can start. Because I think really one of the things you said is about complexity. And you mentioned that simulating the array with 16 atoms was already hard, right?
Yes.
But then you showed an algorithm, right, to look only for the possibility of having the superradiant bump.
Mm-hmm.
The question is whether this is the right question to ask or not.
Mm-hmm.
Because sometimes, depending, of course, on the question you ask, you will get something which exploits the true complexity of the system or not, right? Mm-hmm. The fact that you have something that already with 16 atoms is kind of hard to simulate, mm-hmm, raises a question of supremacy, where with arrays with 60 atoms or so, if there are things to parameters or things to calculate or simulate that you would of course get from the atomic system from doing the experiment,
I mean,
but
yeah,
which would be extremely hard to simulate on a classical computer.
For sure. I mean, yeah, even to know, this is exactly what I meant, right? Like if you take a 10 by 10 array, so it's 100 atoms, you could ask, if I excite all of them, will I see this peak of emission or not? These are many-body problems. So it's usually quantum simulators are used to simulate Hamiltonians, but you could say, well, this is a problem that in my computer I have no idea on how to answer, and in the experiment I put a detector and I measure it or not. So definitely the experiment will give you the answer that a classical computer cannot give you the answer for. And why we bypass this complexity is, of course, we have to pay a price. The price is that we can tell you if we're like above a certain distance, you're not going to have superradiance. We can tell you this. But what we cannot tell you is how large is going to be this peak and when it is going to happen. So of course, like it's not that magically, we can solve this problem with so easily. Is that, kind of by being smart of, what the crucial thing is, because this is like an avalanche problem. If you understand the beginning, you have a lot of clues. It's going to happen or not. That's the question. But we cannot tell you, how big is the avalanche, at what point the avalanche is like going at the fastest rate. We just are going to tell you, here you will have it and here you will not. But that was a question that, people couldn't answer for a long time, because as I said, I mean, it's a complicated problem. And if you try to answer it using, these dynamical equations, it's unsolvable, basically.
Maybe the question there is also, can you sort of classify complexity, use these systems as playgrounds to really make classifications of complexity regarding the problems and the questions that you're asking, and really classifying, because that's obviously an issue in terms of computation, in terms of gain in quantum versus classical systems.
Yeah,
See what I mean?
Yeah, so I don't know if I see what you mean or not. Let me answer just with a comment, and then maybe you can clarify. So I think definitely, because we can answer it, definitely knowing whether you are going to have superradiance or not is not an exponentially complex problem. The whole dynamics of superradiance is an exponentially hard problem, probably. I mean, it's also not clear, right? Because you could think, well, now what if I do these dynamics and then I start truncating, like, it's like I have like all these degrees of freedom, but then maybe not all of them are relevant. So I start doing like smart truncations of the Hilbert space. I try mean field, I go beyond mean field. So like it is not guaranteed that it's you cannot get this curve basically of emitted intensity with exponential complexity. Solving the evolution is a problem with exponential complexity. I don't know if exactly getting the shape of superradiance is a problem that involves exponential complexity. Definitely more than linear, for sure. Because with linear, you can only know if it's going to happen or not. But yeah, I mean, we have been talking with a group in Harvard where they they go a bit beyond mean field to try to answer this question. So they try to get things like the scaling of the peak with atom number and so on. And, it's also work in progress for them. So, I mean, I don't know if I answered your question or I just went on a tangent.
No, part of it, yes. Part of it, yes. There's a question in the chat, actually two questions from Sergio Muniz, who unfortunately had to leave. But he said he's going to look it up afterwards on YouTube, so you can answer, and he won't be able to make any comment on your answer, but he will at least be able to.
He can write me an email if I don't answer it.
Yeah. So the first question is: in a circular atomic array, does the topology play any interesting role regarding Dicke superradiance? For instance, if one thinks of it as an infinite 1D system, with boundary conditions.
Yeah, that's a great question. And this is a question, if you read, so there is this review paper by Harosh, 1982, I think. It's very long and nice paper. And, it reviews, the state of affairs back then. And they were for decades concerned about the geometry and topology, like what geometries would preserve superradiance versus what would not. And so they thought that a ring would, because a ring doesn't have edges, right? So they were very concerned about this dipole-dipole interaction, which they call just the coherent part, the Hamiltonian part. I mean, everything is dipole-dipole interaction, but they focus on the Hamiltonian part that scales as 1/r cubed in, that's the near field interaction. So they thought that this would produce dephasing. And so they said, well, the fact that you have a chain, it means that the atoms in the bulk, they see the neighbors differently from the atom in the edge, right? Because the edge doesn't have neighbors on this side. So this is going to produce relative dephasing between the atoms, and it's gonna destroy superradiance. And in part, this is a bit true. Like there is the Hamiltonian. I mean, I think I have it here. Yeah. So if you see, this is the this is the ring. So the ring actually should go the Hamiltonian without Hamiltonian should be basically the same. It's just that this ring is very tiny, but the ring is slightly better than the chain, but barely better, because what destroys superradiance. So if we go here, this is the example. So this is ring versus chain, and in the thermodynamic limit is exactly the same. the critical distance doesn't change on the ring versus the chain. And this is because what produces the destruction of superradiance is not so much the Hamiltonian interaction, but also you would say that this interaction in the thermodynamic limit, the edges are less and less relevant. But what happens is actually that you have many free space optical modes into which you can decay. So superradiance is again a process of avalanche. So when you want the same jump operator to act continuously, when now a different jump operator, which means radiation in other direction, acts, then this produces, instead of like imprinting more and more times the right phase, it starts to imprint a different phase in the atoms. So this produces dephasing, and that is what leads to the quench of superradiance. So both, rings and 1D chains, when the distance is large enough, the atoms can decay into many, many modes, and so superradiance is not protected by the geometry. It's protected, by the topology. It is protected by the dimensionality of the array. So 2D arrays work much better because they actually cancel emission in way more directions than 1D arrays, and the same for 3D. But it's a very good question because it's a question that has been asked many times in the literature. So our answer is no, it does not change.
The second question is, what if the atoms are in a coherent collective ground state, such as in a BEC?
So if they are in a ground state, they would not emit. Yeah. So let me answer as like a collective spin state, like a coherent spin state. They might show superradiant decay. We know that depending on, so if you prepare a collective spin state, you can imprint certain phase in the atoms, and depending on this phase, the long time dynamics is going to be different. This we know for sure, and if you are interested in this, you can look at the PRL of 2020 that I cited later. But for us to do calculations in this situation is extremely hard. So why we can solve this problem again is because we start from a very special initial state that has no coherence. If you start and has no holes, like all the atoms are excited, if you start having all superpositions where like any number of atoms can be excited, you run into issues with our approach, in the sense of we don't have a clean, easy way to calculate G2, which is what we need to calculate the critical distance. So correlated dynamics is going to happen. Maybe cool things are going to happen, but we cannot use our idea to compute it, to compute for large atom numbers.
I'm looking, I don't see any hands raised, and I don't see anything on YouTube. So I'll ask another question. You mentioned self-organization through dissipation.
Yeah.
There's with superradiance, I always like to bring together subradiance.
For superradiance to happen, subradiance is a key element. You need to suppress decay channels.
Right. Yeah. But the question is,
without the other.
The question actually is, in many ways, the emission can be coupled with, or is coupled with mechanical effects on the emitters, right?
Yeah.
So can you have self-organization in a system where your emitters are free to move, whether they could self-organize in a way that the array that you get is subradiant, but in all directions, meaning that it would be really trapped in a certain configuration, which comes about because, of course, you can tailor this with boundary conditions, for instance, to choose the array. But have you looked at things like that?
Yeah, so, well, first, just purely decay can produce this trapping. So that's the first thing. But you're saying that as the atoms radiate, they're going to move, and there's going to be a spatial self-organization. So the answer is yes. And ideally, I guess this is true that you could, I thought about this in a kind of atomic waveguide configuration where you have a pulse that is propagating, and as it propagates, it changes its own group velocity, I guess, or it changes the medium, right? Like it moves the atoms. So if it moves the atoms, then the refractive index locally, if you can define such a quantity, is gonna change. So it can self-drop. So that's how I started thinking about this. I think this, I don't know if you can trap yourself into a dark state. It might be possible. The issue is it's extremely hard to calculate this for many excitations. Like you can calculate self-organization for single excitation, but if you calculate for many excitations, it's on top of the excitation dynamics, which is 2 to the n, you have like all the atoms moving, so it's horrible. But in principle, for one excitation, you could calculate this. I mean, I think it's an interesting and also important problem, because here we're considering that you are in this like a really strong non-decay regime, that the atoms are really not moving around and they are frozen. But in principle, there is recoil. So like how recoil affects emission is an important question. So it's something that I think is worth looking into, but we haven't yet gotten to that.
Okay, are there other questions or comments? Otherwise, let's thank Anna for a really great talk and for the time.
So much.
Mauricio,